All right, let's get started. Okay, so I hope you recovered from the exam, and I hope you feel it was a reasonably fair exam for what we covered. Yeah. Okay, so we're going to change some direction, right? We're going to enter the middle half or middle portion of the course where we're going to discuss algorithms, right? So for those of you who found the first part easy, this may be a little different, right? If you look at historical scores in 374, not everyone who does well in midterm 1 does well in midterm 2, which is on algorithms, and vice versa. So if you found the first part maybe a little tough because you're not used to that kind of thinking, but you're comfortable with algorithms, you may be fine in the second part, right? So the two are linked, but the skills are slightly different. Some people are more creative with algorithm design. Some people are more comfortable with formal reasoning. They're not the same skills. And so for those who had a tough time in the first part, don't be discouraged, right? It's a part of the learning process. And think about algorithms again, fresh. I mean, for those who did well in midterm 1 or felt comfortable, don't get complacent, because the algorithmic skill is a little different, right? I've seen people who did really well in midterm 1 tank in midterm 2 and vice versa, right? So I mean, it is a tough course, but it's useful skills for you, whether you go to industry or go somewhere else, okay? Or even do, I don't know, law or business or something, right? Okay, so let me, because we're going to change tacks, talk a little bit about algorithms, what we're going to do, and we're going to come down from models of computation to solving very nitty-gritty specific problems of interest, okay? And I mean, algorithms solve specific problems as opposed to worrying about the big picture of what is a computer, what can be done, what cannot be done without regard to efficiency and stuff, right? We are now interested in efficient algorithms. And algorithms are abstractly defined as procedures that run on some mathematical model with some basic simple operations. Okay. Now, what are these simple operations? And so there is some difference between algorithm design in an abstract model of computation and the very low level Turing machine level things that we talk about, right? And the reason for that is basically practicality, right? We can build machines for special purpose things that can give us primitive operations which are maybe fast. And then we want to think about algorithms in the model where we have access to some operations which are a bit high level, right? And so the model of computation matters when you think about efficiency. So what is the model of computation we'll use, right? So we've defined the Turing machine model of computation, and we kind of discussed that it is a bit too low level for our comfort, right? It is like assembly language programming, right? And we don't want to stay at that level, right? And moreover, I mean, because it has its strengths, but the weakness is that it's too low level. So how can we be at a bit higher level but not too divorced from thinking clearly about the algorithm's complexity? So we'll play this game, as many things in practical life, we have to compromise here, think, but keep in mind, at the back of the mind, where we are making compromises and why it's important in some cases to pay attention, right? So it's not as straightforward as it looks, right? So what is it that we will use? At a high level, we are going to think like we are programming in Java or C or any high-level language, right? So what does it mean, right? When you program in Java or C or something, what do you kind of implicitly assume, right? The thing that you implicitly assume is what's called the unit cost random access memory model, okay? So, I mean, it's very, I can formalize it, but roughly you know what it is in the sense of you program all the time. So this is familiar to you, right? So in the RAM model, the basic unit of data is an integer, right? You kind of say int, right? And you don't pay attention to whether int is how many bytes, right? So you assume that you have access to somehow an integer data type, right? And you also have this assumption that, and that integer fits in a word, right? And you have this abstract notion of that it fits in a word. It could be 64 bits right now, it could be 128 bits, 5 years from now, or whatever it is, right? So you have that notion of a word and that an integer fits in that word. And you can do comparisons, arithmetic like addition and subtraction, and even multiplication in unit time on words. That's the abstraction the programming languages give you, right? You multiply numbers, you add numbers. And you also have this notion that you can index into memory using words, right? Whenever you say, array of 10,000 numbers and you use a of I, what does it mean? You're assuming that you can access indirectly the 100th word in the array in unit time. Yeah? You say, a of I times a of j. Right? What does it mean, right? So that means that you're able to indirectly index into this array by specifying I, which is itself a word, right? So that indirect addressing is what you allow. And you also have this pointer-based data structures, right? Again, they are also under this assumption that I can store the address of what I want in one integer, and I can indirectly access that in constant time, right? That's what pointers are, right? Okay, so this is what we'll use roughly, okay? So this is that all this can be done in constant time, right? But so take an example of sorting, right? Suppose I want to sort n numbers, okay? What do we think, right? We say, the n numbers are stored in some array, then I can access any number in constant time, I can compare them, I can swap them, right? So all this takes constant time, right? But that's okay, that's a reasonable model, but it's not a reasonable model when we think of certain other applications. But we have to be a little bit careful about some of this operation, bitwise operations like OR, XOR, shift, right? I mean, for basic simple things like dividing by 2, it is okay, right? Because we shift once. But more complicated functions can create some issues because we can do things with them that, because we are not paying attention to the running time. Okay, so I mean, for the most part, it is fine to work in this model, right? Why is it? Because it reflects for many problems. This is a reasonable model of computation, right? But you have to be careful, right? You have to be careful because we are in computer science, right? And we are not a Joe programmer who doesn't know the theory or how the computers are built. It is our duty to be more careful than somebody who is just programming, right? What does that mean? That you have to be aware of where the model of computation is critical, right? So things like, if you keep on multiplying numbers, you'll overflow, okay? Okay, even simple calculations like if you want to do Fibonacci of 200, you will overflow, okay? You cannot store Fibonacci of 200 in your word right now, right? Okay, that's something that you should be aware of, right? If you keep on multiplying or even adding numbers too fast, you can create bigger and bigger and bigger numbers, and then my model of computation of unit cost RAM is not right because I'm overflowing in the number of bits, right? So that's something that you have to be careful about. Whenever you multiply numbers or do recursion, you have to wonder about, are my numbers going to be okay? Okay, that is something we have to be careful about, right? So for some other numbers, it doesn't make sense to use this model. For example, if I say, what is the complexity of multiplying two numbers? You can't say it's constant, right? If you say it's constant, then we're not thinking correctly because, you can't obviously multiply any number of numbers in constant time, right? Yeah? So when we actually want to examine the complexity of arithmetic, like, how long does it take to multiply two numbers? The right model is not unit cost RAM because, if you can multiply, 10,000 digit numbers in constant time, that doesn't make sense, right? You can multiply any number, right? So I ask you the following simple problem, right? I give you a number and I ask, design an algorithm to check whether it's a prime number. Okay? Everybody knows prime numbers, right? Yeah? So I ask you, I'll give you a number and say, write an algorithm to check whether it's a prime number. What will you do? Okay? And you may say, why do I care? Okay? Well, every time you use SSL, there is some prime number business going on, right? Whether you know whether RSA or not, all our security currently is based on working with prime numbers, right? Okay? So maybe, you say, okay, you have a computer science degree and, somebody comes and says, tell me an algorithm to check whether a given number is prime because I need it to implement some RSA. Okay, what will you do? Yeah? Lookup table. Okay. Why? I mean, why will that work? I mean, I give you a number and you have to check whether it's a prime number, but I'll give you a number bigger than your lookup table. Yeah. I mean, that's the notion of a problem, no? What does it mean to be a problem? It means that I can give you an input of arbitrary size and your algorithm should work on it. Yeah? I can't, if you can't store, so how many digits do you think the prime numbers that we use in our security are? You know? Yeah, so I'm a theory guy, right? You think, why do you need proofs, right? But you're practical guys, tell me, right? Yeah? Yeah, they are between 128 and 512 digits, okay? Why are they so big? Why are they so big? So you cannot do brute force computation, right? The reason why we are relying on them is because the adversary cannot do brute force computation. So can we store all prime numbers of with 512 digits in a lookup table? You don't have atoms in the universe, right? Okay, that's why you need algorithms, right? Okay, given a number, how do you check whether it's a prime number? Okay, well, the obvious algorithm, right? How do you know whether the number is prime? You say, okay, from I equal to 2 to n minus 1, I know how to do division, right? You check, right? Okay, why is it not a good algorithm? Yeah? Oh, n divided by 2, okay. Saying I can even go up to square root n, right? I'll be a little bit more clever, right? You don't have to go check beyond square root n, no? If there is a divisor of a number n, one of them has to be less than square root n, right? So you can say, for every number between 2 to square root n, I will check if that number will divide n, and if it does, it is not a prime number. If I don't succeed, then it is a prime number, right? Is it an efficient algorithm? Why not? No, is it square root n times square root n divisions? Yeah? See, that's why this is important, okay? Imagine your number is 512 digits, right? How long will your algorithm take? So what is the size of your input, right? What is the size of your input? 512, right? Okay, but what is square root n? Yeah? Yeah, so you want to go up to square root of 2 to the 512, right? Okay, that is 2 to the 256. So your running time of your algorithm is 2 to the 256. You will not finish that algorithm, okay? So when you think about algorithms for arithmetic, like, the size of the input is only the logarithmic in the actual number value. Right? See, the number takes 512 digits, right? But the number itself is 2 to the 512, right? The square root of n is too slow. So this is a completely useless algorithm. Okay? It will not finish, in our lifetime, right? So that's why this is not so even something as simple as checking whether a number is prime is not easy to do if you just do the naive thing, right? And so what do people do in practice? Because they are actually, to implement SSL, they are doing it, right? So your algorithm should not be polynomial in 2 to the 512, it should be polynomial in 512 digits, right? That is the size of your input, okay? So checking whether a number of prime is not an easy task actually. You need number theory, right? So there is an efficient algorithm for it, and that the first deterministic algorithm was discovered only in 2002, right? Till then we did not have even a deterministic algorithm. We had to rely on randomized algorithms which had some small probability of error, okay? So all our SSL stuff was using these randomized algorithms which had a small probability of error, okay? So because it's not because people thought that was the right thing to do, because they did not have an algorithm to even check whether a number is prime, which is polynomial time, okay? So what I'm trying to say is that depending on the problem, you cannot simply think that the unit cost RAM model is the right one, right? When you think about prime numbers, you should say, the problem is different. I need to think about the number of digits in this problem, right? That is the size of the input, not n itself, okay? So when number problems are there, you have to be very careful, okay? That's all I'm trying to say in this thing, okay? So in this class, because, we have to trade off between working with sorting and working with primality, we'll for the most part work with this assumption that you can add numbers in constant time, multiply numbers in constant time, except when we worry about the representation of numbers, right? When there are weights on the numbers attached, you have to be a little more careful, okay? Okay, so, and even this unit cost RAM model is not quite accurate, as you know, because you can overflow and stuff, so you also have to be a little careful on when. So what I'm trying to say is that life is complicated, and it's not because we want to make it complicated, because we want to play this game of how close can we be to reality in terms of design of algorithms versus subtleties involved when problems get complicated, okay? That's the bottom line, okay? So there will be three, so roughly it's good to categorize the kind of problems you will see in not just this course, but in general, right? It's good to have a mental model of the type of problems you'll see in this course, right? Or any problem, that's right. So some of the problems are of the following form, right? They're decision problems. The answer is yes or no, right? So what is a simple example, right? So I can give a graph and I say, S and T, and say, is there a path from S to T, right? So I'm not interested in finding the path, but I'm only interested in yes or no. So those are called decision problems, right? Because the answer is Boolean. The other problem is what's called search problem, right? The search problem associated with something is like, given a graph in S and T, if it is S can reach T, give me a path connecting S to T, right? So I actually want you to give me a path when they're connected rather than just saying yes or no, right? That's a search problem because you're outputting a solution, right? Not just a bit. And what is the optimization problem? Many times we'll encounter optimization problem. Shortest path problem is an optimization problem, right? Why is that? Because there could be many paths from S to T, right? And we want to find the best path, right? What is the best path? You define it as shortest because you cared about shortest path. Maybe I'm interested in the longest path, right? So what I'm trying to do is, I'm going to assign some values to these paths by either lengths on the edges or however we define, and we want to find the best according to some value function, right? So these are the types of problems we'll encounter in our class, and in general, high level, these are interesting problems to keep in mind. So as you do algorithms, it's important to know, as you can see, these problems, for any given problem, this should be the easier version of this, and this should be the easier version of this, right? Okay? So it's important to know, suppose I ask you to solve an optimization problem, and maybe you're stuck. You say, okay, look, I'm finding it hard to think about the optimization problem. Let me see if I can solve the search problem and see if I can understand the problem, right? And maybe you're even having a hard problem with the search problem. Maybe then you go to decision problem and you see if you can solve the decision problem, right? So the idea of simplifying problems is important, okay? Okay, and why do we design algorithms? Because we want to solve practical problems, right? For the most part. So how do we measure whether my algorithm is better than your algorithm, right? Or your algorithm is better than somebody else's algorithm, right? So we measure for the most part in these theory classes by asymptotic running time analysis that you have seen, which is that how much time in the worst case does this algorithm take, right? So what does that mean? That means that we say, the running time of an algorithm is f of n if for all inputs of size n, the algorithm stops in time O of f of n and gives you the correct answer, right? Okay, So that is the worst case running time, right? Maybe your algorithm runs faster than average, but we use worst case measures because it's a robust notion of measurement. Sometimes we worry about space also. How much space does the algorithm require, right? It could be data structures and so on. Okay, so what are the techniques that we are going to cover in this class, because we only have finite time. One of the most important things which will be implicit throughout the course is the notion of a reduction, right? We don't want to create new algorithms all the time, right? It's very hard to create nice new algorithms all the time, yeah? Because how do you verify that they're correct? How do you code them up, right? It's always difficult to create new algorithms from scratch. So that's just from a practical point of view, but also from a theoretical point of view, you want to rely on existing algorithms as much as possible so that you don't have to reason very often for new things. So reducing a given problem to a known problem is always a good strategy, right? You don't reinvent the wheel, okay? And part of the reducing to a known problem is sometimes you cannot, right? Maybe it doesn't look like a known problem. And so one of the most powerful techniques to solve any problem is recursion, right? To try to reduce the problem to itself, a smaller instance of itself, right? And there are many variations of recursion, including divide and conquer and more in the powerful notion of dynamic programming that we'll cover, right? And then we'll see some graph algorithms. You have seen already graph algorithms in 225 and other places. Graph algorithms are very powerful, not only because they solve some fundamental problems, you can use them in many powerful ways via reductions, okay? They provide a lot of reductions. And then we'll also see some greedy techniques, okay? How do you design greedy algorithms and stuff? There, of course, the landscape of algorithms is very vast. We're not going to cover many things because there's no time. Yeah.
States come up again in algorithms?
They will. Yeah, you can think, yeah, states will come up, right? We'll see, okay? Okay, so that's kind of a preview of what we're going to do. Let's do some introduction to recursion, okay? But before we do that, let's do some reductions, right? What does it mean to do a reduction? So you want to solve problem A, right? And A looks like something is new. I have not seen this before. But you have a bag of things that you already know how to solve, right? You know how to solve sorting, maybe you know how to solve some graph problems, and so ideally you should reduce your problem A to problem B so that you don't reinvent the wheel, right? So, here is a joke, right? How do you hunt a blue elephant? Okay, it's a blue elephant gun, right? And this is Ariel developed this, so I like this. So how do you hunt a red elephant, right? Okay, hold his tongue shut until he turns blue, and then shoot him with the blue elephant gun, right? So that's, right? How do you shoot a white elephant, right? Embarrass it till it becomes red, right? Now use an algorithm for hunting red elephants, right? So it's like that, right? You don't invent new things, right? That's how you do it, right? Okay, the key step is this, right? Embarrass it till it becomes red. That's how you convert white to red, okay? All right. Okay, now let's do a simple example. Something that you understand very easily, unlike elephant hunting. So given an array of n integers, are there any duplicates in this array? Are all the elements or numbers distinct? Or are there two numbers which are the same in the array? Hash map, he says. No hashing allowed in this class. Okay? Not because I don't value hashing. Okay? No hashing allowed. I'm announcing it. If you use hashing, you'll get 0. Okay? Because the reason why I do is not because I don't think hashing is valuable. It's because understanding hashing properly mathematically is not so obvious. Okay? Right? You can use hashing, it's a practical technique, but in this class, you're not using hashing. Okay? All right? Okay, no hashing. So what do you do? Okay. Okay, saying in a sort end, do a linear sweep, right? So that's correct, right? If you didn't know, how would you do? If somebody, you gave it to, when you were taking, 125 and you didn't know how to sort, what would you do? You would walk through each one and do the obvious thing, right? Take the first guy and see if there is any copy of that in the entire array, right? And take the second guy and do it, right? So that'll take n square time, right? Okay, but now that you know sorting already, right? You're like, okay, I can do sorting, and then I can do only one sweep of, right, the array once I sort, right? Okay, So why is it useful? One is that, the running time is O of n plus the time to sort, right? The point is that you don't really know or care how the sorting algorithm works, right? It could be a fast algorithm, it could be a slow algorithm, but conceptually, you can reduce this problem to sorting, right? So that's just a reduction, right? That is the idea of your reduction, is that you use it as a black box, right? Okay. What is it? You may say, is there any advantages of the previous algorithm compared to this algorithm? You have to, again, be careful, right? So the previous algorithm did not assume that objects are necessarily sortable, right? Right? Only thing that the previous algorithm used was that you can compare two things and check if they're equal. Okay? Sorting requires you to be able to compare every pair of elements, right? So hashing is a good idea. Okay? Why is hashing a good idea? Suppose I give you a whole bunch of images, right? And you say, are there two images which are the same? Right? So what will this algorithm do? It will try to do what? It will try to sort the images, right? Yeah, how do you sort images? You can. Why can you sort images? Yeah, why can you sort images? I think you can, yeah. Yeah, so everything you represent in an object is a string, no? So you can always compare two objects. But is it practical? No. Okay, so hashing is good for that reason, right? Okay, but hashing is again tricky for mathematical reasons, right? So it's not always obvious what is the right algorithm to do, right? All I'm saying is that the worst case analysis is good for running time when it is integers which you can sort, but depending on the problem, you may have to think about different techniques. Yeah. Why hashing is? Oh, it's because to do hashing properly and to analyze hashing, how it behaves, you need randomization. If you always use the same hash function, it will behave very badly, right? So the underlying assumption in when you use hashing is that the data is random or you're using a random hash function. Okay, now you have to say, how do I understand randomized algorithms? Well, you need some tools for that and formalize the model. Okay, so if you take 473, you will learn some of that, right? So it's fine to use hashing in practice, but we discourage it or we do not allow it in this class because we don't know how to analyze it mathematically at this point, right? That's the only reason, okay? Okay, so there are two sides of reductions, and then we'll come back to this again and again, right? One is the reduction as an algorithmic design tool, right? We reduce the problem of distinct elements to sorting, right? So what does it tell us? If sorting is easy, distinct elements is easy, right? Okay. But we also get the second implication, if somehow I knew that distinct elements is itself hard, then I'll get the conclusion that sorting must be hard. Yeah? Okay, we'll come, this will come back to us, because this is a thing that will happen in reduction. Okay, more examples on reduction. So here is a graph problem that we'll see again and again. So here is a graph. Everybody knows what a graph is, I assume, right? At least informally, it's an undirected graph. So there is a notion of what is called an independent set in a graph. What is an independent set? A subset of the vertices such that there are no edges between them. Okay. So what is a subset of vertices that don't have any edges between them in this graph? What are examples? Any vertex is independent, right? Okay, I claim A and D are independent. A and C are independent, right? Okay, A, C and F are independent. Yeah? You agree? Okay, so what is the problem I want to solve? I give you a graph and you have to give me the largest independent set in the graph. Well, in this graph, what is the largest independent set? Is there an independent, we saw an independent set of size 3, right? Is there an independent set of size 4 in this graph? Yes or no? Yeah? I don't think so, but yeah, it's a hard problem actually, right? Right? It's not an easy problem. It's an NP-hard problem. We'll come back to it. Okay. All right. So it seems interesting problem. Yeah. Okay. Okay. Now that's an interesting problem. I can also put weights on it, right? Maybe this guy is more useful than this guy. Then you can ask, find me an independent set with the largest weight, right? Okay, you can ask that. So here is another problem that you will probably see in some application. This is called, so I give a bunch of intervals, right? So these could be, jobs, right? So this job starts here and ends there and has value 10. This job starts here and ends here and has value 2 and so on, right? Okay. I want to find, I'm a single person, right? I can only do one job at a time, right? I want to make a lot of money, right? So what jobs should I take in this sub collection so that I can do them? See, I can't take two jobs which overlap, right? Because then I can't do them, right? So I want to maximize my profit. So I want to find a largest subset of these intervals, the highest weight. So I make the most money, right? By doing all of them one by one sequentially, right? Okay. So I can do these three jobs, right? How much money will I make? 21, right? Maybe there are other solutions, right? I can do this, and this, right? How much money will I make? Okay, I'll make 8, but this is clearly better, no? Yeah. So I want to find the best thing for myself, right? Maybe somebody asks you to solve this problem, right? Okay. So are these two related, by the way? I want you to think, is this problem somehow connected to this problem? Which problem looks more abstract and more powerful or general? Sorry? This one, yeah? Or okay, how do we formalize that? So can we say that, to solve this problem, if you had an algorithm to solve this problem, you will be able to do it? How? I don't know how to solve this, but suppose somebody, my friend said I can solve this, I have code for this. And you want to solve this problem. Yeah, that's what I'm saying. That's called a reduction. How do you relate this problem to this problem? What is a notion that, that you can use to reduce this problem to this problem? Yeah, that's right. You see, right? You create a vertex for each interval and put an edge between them if they overlap. Yeah? Yeah, easy enough, right? Agreed? Okay. So that's called a reduction, right? We took this problem, which looks new, but somehow if you knew that this could be solved, you can easily solve this problem, no? Yeah? That's the reduction, right? Okay, good. Okay, so that's all reductions are. Okay, so what about this problem? Okay, what is this problem? It looks like now the intervals are arcs on a circle. Yeah? Same problem? Okay, you have to be careful. Okay, so I have a circle and I have intervals on the circle, right? Like yeah? Now I want to pick arcs which don't overlap. Is the problem clear? Yeah? So, okay, let's try to understand. Can we solve this problem using the graph problem? Yes or no? How is this problem okay, so I'm saying, you saw that you can solve this problem if you can solve the graph problem, right? What about the interval, this problem? Yeah? It's the same reduction, right? It is right. You put a vertex for each arc. If two arcs overlap, you put an edge between them, right? Yeah? You can reduce this problem to the graph problem, yeah? Is that clear? Okay, now, but let's see. What about this problem and the arc problem? Yeah, okay, so I mean these two look more closely related, no? This the arc problem and the interval problem. Okay, so can you reduce this problem to the arc problem? Yeah? Yeah, good. So you take this line and wrap it around, right? Yeah? I mean, okay, that's informal. Yeah? If I take this and kind of stretch it and make it into a circle, no, each interval becomes an arc and we'll be fine, no? Yeah? I mean, informally, yeah? Do you see that the interval problem is can be reduced to the arc problem? Yeah, by imagine that this line is a small portion of a huge circle. Yeah? Yeah? Think of this is a small portion of this infinite circle, right? Yeah? Then all this become arcs, right? Yeah? So this is a special case of the arc problem. Yeah? Agreed? So if somebody solve the arc problem, you can solve this problem, right? Okay, can you go the other way? Yeah, if you solve this problem, it is a special case now. The arc problem looks more general, no? Yeah, this is simpler, right? Yeah, because we just argued it's a special case. Because why? We can take this line and make it look like a big, if you put it in the circle, then, it's clearly a special case. But life is hard. Your friend has code for this and you want to solve this problem. What will you do? Yeah? Yeah, that's showing that you can reduce the interval problem to this problem. Yeah, so he's saying, maybe I can convert this into the interval problem. How do we do that, right? Because, on a cycle, they can all overlap, right? Okay, here is one hint, right? Suppose there is some point in the cycle that is not covered by any interval. Suppose, my example looks a little different, right? I have a cycle like this, but my arcs only look like this. Okay, can I then reduce it to the interval problem? Yeah? How? You cut open the cycle, right? Yeah? You say, okay, I'll cut this cycle here and then, yeah? Okay, but life may not be so simple, no? So what do you do? Yeah?
For any segments that are overlapping and would get cut in half by your arbitrary you just duplicate them on either side and then map them to the center.
But can I do that? Okay, so here's the right idea, roughly, right? So if this is an easy case of the problem, if there is a point on the cycle that is not covered by any interval, I can cut it open, right? Yeah? So, okay, so what you could do with a little bit, this is not obvious, here is what you could do. You try some basic enumeration plus the reduction that we talked about, right? Suppose I knew that one arc in an optimum solution. I don't know, right? Suppose I told you that, look, this guy has so much weight that it is in the optimum solution. What can you do? You have to take it. Suppose I tell you, you have to take this arc. What will you do? Yeah? Exactly, right? You take it. Once you take it, what should you throw out? Everything that overlaps with it. But then I can cut the circle, right? Yeah? If I take this arc, then I can throw all the guys that interfere with it out. And now I can cut this, because I'm guaranteed that this arc is there, I can cut the cycle and reduce it to the interval problem. Okay? Does it make sense? If I knew one interval in the optimum solution, I can cut the cycle like I did before. Yeah? Okay, do I know one interval in the optimum solution? No. So what will I do? I'll try all possibilities for that one interval. Okay? So it's a combination of a bit of enumeration and a reduction to the interval problem, right? So I try all possibilities for that interval, right? Pick one interval, take it, remove everything that overlaps with it, cut out the cycle. Now I have the interval problem, I can solve it, right? And try it for all possible arcs and take the best solution. Okay? So you see, the thing is, even though it doesn't look like it is a straightforward way of reducing this more general problem, with a little bit of work, we could translate from one problem to the other. Okay? That's the notion of a reduction, basically. Yeah.
Can I change the word reduction with transform?
Yes, you can use it as transform. Yeah. If you like transformers, that's one way of thinking. Yeah. Okay? The reductions are very important. Okay. So that is to give you that, reductions can be complicated, right? We'll see even more complicated reductions, right? Okay. Okay. So, see, to do reductions, you need a nice problem that you need to solve, right? That somebody has already solved for you. Okay. It's like having a nice friend who can always solve your homework problem, right? So that'd be nice, right? But you're writing the exam and you can't rely on somebody else, right? So what do? Right? Then you have to reduce it in some way so that you yourself can solve it, right? So that's where recursion comes in, right? Recursion is a technique of reducing a problem to a smaller version of it itself so that it becomes so simple that you can solve it by brute force or some other technique, right? So that is just recursion, right? You've seen many examples of that, and it underpins many techniques, right? So we'll work on that, right? And many times recursion is the cleanest and simplest way of solving problems, and because the proof is very easy because you can use induction. Okay, everyone has seen Tower of Hanoi at some point. Some of you probably have not, right? Here is this puzzle, right? What is this puzzle? It has some discs of different sizes, right? Of n sizes. There are 3 pegs. So the discs are arranged in this order on peg 1, and you want to move all these discs to the 3rd peg one by one, right? What are the rules of the game? The rules of the game is that you cannot put a bigger disc on a smaller disc at any point in this process, and you can only move one disc at a time. Yeah? Some of you have seen this before, right? How will you do that, right? So you want to move all this to this, right? There are n discs. You cannot put a smaller, see, for example, you say I put this here, and then you can't put the bigger one on top of that, right? So because that's the obvious way of doing it, right? You flip it and then try to put it on the, see, if I allow you to put discs as you want, what is the solution? Right, you flip it, right? You put this guy, then the next guy, the next guy. You make all of them go on this side, and then put this guy on back in the reverse order, right? That will take only 2n moves, right? But now I'm not allowing you to put a smaller thing, a bigger thing on top of a smaller thing. So how will we do this? Yeah, right. Yeah, where will you put? YouTube. So now we go to YouTube, right? Okay, but there is no YouTube on the exam, right? You can't. What do we do, right? We are relying on ourselves. No YouTube. Yeah. That's not an algorithm, right? Because see, I can't even, after 3 steps I'm lost, right? Because I don't know what you're saying, right? It's not compact, right? Yeah. Yeah. So I mean, what is saying? If you right, yeah. So, I mean, that's why recursion is powerful, right? You're trying to solve a big problem in one shot, right? That's hard to do, right? We want to simplify the problem and say, can we, if you're going to solve this big problem, we should be able to solve a smaller problem, right? Right? Okay, maybe we know how to solve, if you have 2 disks, you figure out how to solve it, right? Right? Maybe you know that, right? But if you have 3 disks, maybe it's getting complicated, right? So if you see, can I use the 2-disk solution in a black box, right? In my thinking, right? I know how to move 2 disks. I don't have to worry about the precise details of how to solve the 2-disk problem, okay? But I know it can be done, right? Okay, can we then solve the 3-disk problem, right? How do we do it? Well, I mean, once you see the solution, it is looks obvious, right? You say, aha, look, if I can move the n-1 disks to the middle peg, how? Using recursion, right? Because I know how to solve the n-1 size problem. Then I'll move the big disk to the last peg, and then move all the n-1 disks from here to the last peg. Yeah? So the only thing that this is doing is that I'm not worrying about how to solve the n minus 1 problem, right? The nice thing is that I don't want to worry about the details of solving the n minus 1 size problem while I'm trying to solve the nth problem, right? Problem of size n, right? Okay? Does that make sense, right? Yeah? What this did, right? We're thinking recursively. How do I break a problem of size n into smaller problems that I know how to solve, right? Yeah? Okay. So, what am I doing here? How many times do I have to solve the n minus 1 size problem? Once to move to this middle peg, and once after I move once I move the largest peg, disk to the third peg, I have to solve the problem of again moving all these guys from the middle peg to the, but they are the same problems, right? That the pegs have changed numbers, that's all. Okay? So to solve a problem of size n, what am I doing? I'm solving two problems of size n minus 1, and then I'm making one more move, right? Yeah, the big disk I'm moving from, right? So I get an automatic, you can write the code recursively, Hanoi n source destination temp, right? The 1 is a source, 3 is a destination, 2 is a temporary thing that I'm allowed to use, right? So what is it? If n is greater than 0, you solve the n minus 1 problem from source, you make the disks go to the temporary peg using the destination as a intermediate thing, and move the largest disk from the source to the destination, and then move all the disks from 1 to n minus 1 from the temporary to the source, right? To the destination using the source as intermediate, right? The same pictorial thing. So how do we analyze the running time of this algorithm? We use recurrences, right? Right? How do we think if t of n is the time to move n disks via this algorithm? What is the recurrence for the running time? Right? T of n is 2tn minus 1 plus 1, right? Yeah? And t of 0 is 0, right? T of 1 is 1, right? Yeah? Is this clear? No? Yeah? This is just, we wrote down what the recurrence is doing, no? Yeah? How many moves do we make for n disks? Yeah? We have to move this n minus 1 disk 2 times, no? Okay, what is the solution for this? Okay. No, this is driven by this recurrence, no? So how do we have to solve the recurrence. We know how to solve recurrences, right? Yeah, okay. But what is this? Yeah, sorry? Back in the days when we were kids, right? Right? So, but sorry, but we have to become, we have to go back to childhood, not, right? So you can solve this by, the simplest technique to solve recurrence is, do the obvious thing of expanding the recurrence, right? And see if there's a pattern, right? That's the simplest thing you should do, right? If you don't know, you do basic algebra, right? Don't be clever. So you just do this 2t of n minus 1 plus 1. What is t of n minus 1 by the recursion? It is 2 times t of n minus 2 plus 1, right? Plus 1. So you just expand, right? And you get, at the end, the answer is 2 to the n minus 1 plus 2 to the n minus 2 plus 1, right? What is that? 2 to the n minus 1, right? Okay, that's the solution, right? Okay, if you try to think iteratively and say, I'll move this disk, move that disk, your strategy has to use 2 to the n steps, which is very difficult to keep track of. Okay, so you shouldn't do that. Okay, so that's recursion, right? So recursion really helps us abstract out what's going on and not remember all the fine details of what the recursive algorithm is going to do. Okay. You have to learn to trust recursion. Okay? You have to learn to trust recursion. If you try to understand the fine details, then now you're not thinking high level and breaking up the problem. Okay? That's the power of recursion. But then if you try to say, what is the t of n minus 1 doing? Okay, now you're going to get in trouble. Okay? You have to let go. Okay? It's like swimming or something, right? You have to learn to let go. Okay. Okay. So recursion is a very powerful technique, right? It's applied for a variety of things. one of the most interesting ways recursion is applied is to do divide and conquer. Okay, and why divide and conquer? Is basically to speed up computation. It's not, divide and conquer is a strategy to speed up computation than really to solve a problem. Okay, it's to speed up something that we need to do. So in divide and conquer, you take a big problem, you chop it up into many problems, smaller problems, and solve them recursively, and then try to put the solution back together from them. Okay, and the canonical examples of they say, why is this not recursion? It is recursion, but it's a specific technique in recursion. So let's recap the first example that people see in recursion, which is merge sort, right? So it goes back to von Neumann, the great man, right? Even though it's maybe a very simple idea, right? You want to solve the problem of sorting, right? So sorting is easy now. I mean, in the sense, why is sorting easy? In the sense that if I tell you to sort, then you can easily come up with an n-square algorithm. Yeah. So sorting is easy in the sense that coming up with a polynomial time algorithm is not hard. Yeah. Agreed? Yeah. Anybody can sort, right? We all do sorting from a young age, right? But the first non-trivial application of divide and conquer is to say, can we speed up this basic task of sorting that we all do at all the time, right? And if you want to explain to somebody who doesn't do any computer science, right, sorting is a good example, right? To say, you have to be clever about algorithms because the obvious thing is not the right thing, right? And this is the first example, right, of how to speed up an algorithm for a basic task. So how does merge sort work? How many of you have not seen merge sort? At least informally before. Yeah? Okay, you've all seen it, right? But let's review it, right? You break up an array of size n that you want to sort into two arrays of size n over 2 each, right? And you recursively sort them. We trust the recursion, right? We let go and it will do it for us, right? And now the only task that is left is that I have two sorted arrays. I need to combine them into one sorted array. Hopefully it's an easier problem, right? I have two sorted arrays and I want to sort. So how do you do it? Yeah? We all know how to merge two sorted arrays? Yeah? How to do it? Well, we have two sorted arrays. We keep track of a pointer to each array and we compare them and put the smaller one first and we keep moving the pointers, right? And then we get, A is smaller, then we look at G and H, G is smaller, and we keep going like that, right? And then how long does it take? No, this merge step, right? If you had an array of size n and an array of size m here, how long does it take to merge these two arrays? N plus m, right? Because you are just keeping track of one pointer and moving them across, right? Yeah? Okay. So we know how to do merging, right? So, yeah. So this is the code for merge sort, right? Merge sort takes an array of size n and breaks it up into two arrays and recursively sorts them and then does merging, right? Yeah? And okay, merge is kind of looks complicated, but it's the obvious algorithm. It's not hard to understand it. Conceptually, I've seen it. So you say, okay, I'm done. What is how do you prove it is correct? The nice thing about recursive algorithms are they're very easy to prove correctness for, right? Why? We have to use induction. Whenever we have recursion, you have to use induction. Yeah, right? If the base case is single element, it's always sorted. So this is the code for merge sort, no? Why is this correct? Every recursive algorithm, the proof of correctness has to use induction. Okay? Alright? So the base case for merge sort is what? N equal to 1, in which case you don't have to do anything because the code is not doing anything, so it is correct. Yeah? Okay, but why is it correct on an array of size n? Well, if you assume that this code works correctly for all arrays are strictly less than n, you know that this is going to be correct and this is going to be correct, right? Okay. Now the correctness has to rely on what? Merge being correct, no? Yeah? You can claim that this algorithm is correct only if you can convince yourself that merge is correct, right? Yeah? Okay. So your proof requires you to argue by induction that if merge is correct, then merge sort is correct using induction. Okay? But now what you're left with is the task of proving that merge is correct. Okay, how do you prove merge is correct? Sorry? You don't agree that it is, what do you not agree with?
You say to prove that this function, this merge sort is correct, that merge is correct.
No, you use induction to prove this is correct, assuming merge works correctly.
So what if merge was before the first merge sort? Then the function would be incorrect. But by your definition of proving it, all you can do is check to see if merge is correct.
No. I'm saying that assuming merge is correct, I can prove by induction that merge sort is correct.
What if merge is at the top? What if merge first merge sort? Prove it the same way?
No, I wouldn't, right? Because my proof of correctness of merge sort inductively, if merge comes before, it wouldn't make sense because the arrays wouldn't be sorted.
Yeah, that's my point.
Right. But yeah, so that means that what does it mean to prove merge is correct? Merge, what is the definition of merge? Merge takes as input what? Two sorted arrays, not any arrays, right? So if I put merge in front of this, then it is input, you're giving it, incorrect input. So how can you say that you're invoking merge correctly? Right? For merge to be correct, its input has to be two sorted arrays, right? You can't prove merge is correct, this code is correct if it gives you some unsorted arrays, right? It doesn't make sense, right? So to invoke the correctness of merge, you have to give it sorted arrays, right? That you cannot do by putting it in front of it, right? Okay, how do you prove merge is correct? Now you may see that I'm belaboring the point. It's obvious that merge is correct, no? Okay, but see, if you write this code and somebody says, why is this correct, or how do you convince yourself that it's correct? So it's not a pedantic question, by the way. Okay, it goes at the heart of designing algorithms and being convinced that. Why do you believe that this is the correct algorithm, by the way? What is your intuition for why this algorithm is correct? Why is this algorithm correct? You ask, some friend of yours who is not doing computer science and comes and says, hey, can you give me some idea of why this is correct? Yeah? Yeah, so in some sense, this is precisely like why selection sort works, right? You have to prove this by, again, induction, right? You have to convince yourself that, look, the first element I'm putting in this array has to be the smallest element in the entire array. For that, you have to use the fact that this is sorted and these two are the smallest of this, right? And then you have to rely on the rest of the thing working by induction. Okay? So effectively, merge inside it is actually also a recursive algorithm, right? Merging two sorted arrays it's best understood not as an iterative algorithm, but as a recursive algorithm. Okay? You merge two sorted arrays by saying you pick the first element, put it aside, and merge the two other lists, sorted lists, recursively. Okay? All right? So it's important to understand why you need to prove this the correctness of this, right? So even simple algorithms are hard to prove correct formally if you don't think about them the right way. Okay? Okay, so or you can do it by invariance, right? So now let's try to understand how to write the running time of any recursive algorithm, right? You just go look at the code, and that's why it's easy. You say, okay, what is the running time of this recursive algorithm? Well, it's working on an array of size n, right? And it's breaking it up into two arrays of size n over 2, and then it's doing some computation, and that we know takes only n plus some time, so we can write a recurrence for the running time as t of n is a running time for an array of size n is 2 times t of n over 2. In fact, to be more precise, you have to say t of floor of n over 2 plus t of ceiling of n over 2. You can ignore that and then how much time do I take to merge the two arrays? N time, right? Some constant times n, right? So this is the recurrence that we get by looking at the code for merge sort and say, aha, this is it, right? And then what is the solution for this? We all know it's n log n, right? Yeah? Okay, how do we prove it's n log n? Sorry? No, but then, yeah, okay, so in induction, okay, solving recurrences is important not because, they come up, no? So you write merge sort and say, how do we understand what is the running time of this algorithm? Is it any faster than the obvious silly algorithm that I can come up with? We wouldn't know if we can't solve recurrences, right? Okay, we have to, recurrences are not there because they're just out there for fun, right? They come up because we are trying to analyze something that we need to understand, right? You got to get a feel for it. So, solving recurrences exactly is not the point in most of the things we do. We need to solve them roughly asymptotically, right? So the main technique I want you to remember is what's called the recursion tree method, okay? And we'll do that a little bit now. In this solving recurrences, this quote of Einstein is very relevant, okay? Okay, what does it say? Everything should be made as simple as possible, but not simpler. Okay, what is he trying to say in that quote, right? When you want to understand the asymptotics of solving recurrences, if you try to solve them very exactly, it can be painful, right? You won't find so you have to solve them a little bit loosely. I don't care if it is n log n or 10 n log n because I'm interested in asymptotic complexity. But you can be loose, but if you're too loose, you can make mistakes too. So where to draw the line? There's no good thing, you have to do practice, okay? So it's important, and we'll see some examples why this is where this is important, right? So how do we understand recursion? Okay, to understand recursion, we do recursion trees. Okay, so what does it mean? What does this mean? That so I have an array of size n. What is the recurrence doing? It is breaking it into two smaller problems. No, of what size? Let's say n by 2, right? Or even like, if you're very roughly n over 2, right? Yeah, exactly n over 2. If n is a power of 2, you can do this. What is this doing? Okay, so I'm going to adopt this convention of writing the size of the problem inside the what? This circle, right? So the algorithm is taking an array of size n. And what is it spawning? It's spawning 2 children, right? On arrays of size n over 2, and they are recursively spawning 2 children of size n over 4, where n is the size of the original problem, right? How long does it go on? It will go on for a while, okay? Okay, but what is the running time of the algorithm? It is, how long does it take to combine these two to form a sorted array? That is the time that we need to put next to this to indicate that, if I gave you the solutions to the problems that the recursion is generating, how long does it take me to put them together? How long does it take? Yeah, some c n time, right? For some c, let's say c is 1. So n means here, if I had the solutions for my sub problems, I can put them together to create my problem for the original problem, right? So what about here? I need n over 2 time, right? Yeah? I need n over 4 here and n over 4 here, right? So what is the total time the algorithm is spending in all this recursion? Yeah? Yeah, why is that? We have to add up all these numbers, right? Yeah? This guy is taking n time and this guy is taking n over 2, this guy is taking n over 2. Right, this guy is taking n over 4, this guy is taking n over 4, right? We write down all that and we have to add them up, right? How do we add them up? The easiest way is to say, aha, what is the total work done at this level? N, right? What is the total work done at this level? N. What is the total work done at this level? N. How many levels are there? Log n levels. So the total work is n log n. Okay, That's it. Recursion tree method is important to not only understand the running time, but to know when we do dynamic programming, this is very, very important to understand what are the problems that are being generated in this recursion, right? Okay, it's very important that we think of the recursion as generating a tree of problems, and this is the way, one way of thinking about the thing. The size of the problem matters, and this is the total work that this child will do, assuming that it has answers from its children, right? So the total time is n log n, yeah, makes sense, yeah? Okay. So it's important not only to just know the answer n log n, but it's also important to realize that this kind of mathematical formula gives us n log n, right? So that when you think of a new algorithm, you say, oh, if I did this, I will get this kind of running time. So the feel for recurrences helps you design algorithms, or at least think of algorithms, okay? And we'll see that next lecture on some, how that, so this will be on the homework, so don't worry about that. Let's do quicksort, because quicksort is also simple enough. Everybody has heard of quicksort? Yeah? Who hasn't heard of quicksort? Just to know, right? Okay, quicksort is another sorting algorithm, right? It's also divide and conquer, but it's a little bit different divide and conquer, right? In merge sort, we broke the array, recursively sorted it, and then had to put them together by merging, right? Okay, in quicksort, we split the array first into pieces that we know will be separate, and then we recursively sort them so that we don't have to merge them together. Okay, so how do we do that? So, so here is the example. So here is the array that we want to sort. What quicksort does is it picks one of the numbers of the array. In the regular implementation, it just picks the first element in the array, right? And splits the array into two pieces, all the numbers less than that pivot and all the numbers bigger than that pivot, right? So what are all the numbers less than 16 in this array? So it says, okay, 12, 14, 5, 3, 1, right? These are all the numbers less than 16. And what are the numbers bigger than 16? 20, 18, 19, right? Okay? And now we know that in any sorting of this array, 16, all these numbers should come before 16 and all these numbers should come after 16, right? So we can sort this recursively and put them together. Okay? So that is quicksort, right? Yeah? Okay. So what is the advantage of quicksort over merge sort? Or is there any advantage? Sorry? Yeah, okay, so why do people use quicksort in practice, you think? Sorry? It's in place, right? That's the reason people use quicksort, is that you can do this pivoting without creating a new array. Okay? With one linear scan, you can do this pivoting, right? Okay? Yes? So that's very important in cache performance, and that's the reason why. Okay. But what is the worst case performance of quicksort? It can, in the worst case, take n square. What is the really bad example? If it is actually sorted, right? If the array is completely sorted, what happens? And you pick the first guy as the element pivot, what happens? You get all the n-1 elements staying where they are, no? Okay? So if my array is actually 1, 2, 3, 4, 5, up to n, and I pick 1 as a pivot, what happens in quicksort? 1 stays, and all this array stays the same, no? So what is the running time of the algorithm become then? T of n is? So what is the running time of quicksort as a recursive algorithm? It is a recursive algorithm, no? Okay. Well, it depends on the pivot, right? The running time of quicksort can be expressed recursively as T of n is what? We recurse on two arrays, okay? What are the sizes of the arrays? I don't know, right? It depends on the pivot, right? Okay. So if the pivot is rank k, that means that it is in the kth position, that means then the one side of the array will be k minus 1 and the other side of the array will be n minus k minus 1, right? Okay. So it depends on the pivot, and so we don't get a nice recurrence, right? Because it's not a clean recurrence that we can solve because we don't know what the pivot is, right? But in the worst case, what does it become? If you always pick the pivot with rank 1, then it will become t of n is t of 0 plus t of n minus 1 plus n, right? If you always pick the bad pivot, and what is the solution to this? This becomes t of n is n square, right? Why? Because t of n is t of n minus 1 plus n. What is t of n minus 1? T of n minus 2 plus n minus 1. So it will be n plus n minus 1 plus n minus 2 up to 1, that is n square. And we know quicksort can take n square time in the worst case, right? Why do people use it in practice? Not only for the fact that it is in place. If it always gave n square, people wouldn't use quicksort, okay? The reason is that, under a randomization assumption, it will run in n log n in the expected time, and you can actually make it run in expected n log n or even with high probability by picking the pivot randomly. Okay, so that what happens if you pick the pivot randomly? The two sizes will be roughly balanced. Okay, and then you will get n log n because we have taken the problem and broken up it into roughly equal pieces. Okay, so that's why people use in quicksort so binary search, I assume you will read on your own, but let me solve a couple of recurrences for you. This looks interesting, maybe. How will you solve this? What is the difference between merge sort and this? Instead of n, it is n over log n. Hey, what is going on here? Okay, we just do the same thing we do. What do? We draw some circles, right? You like circles, okay. So what is the meaning of this recurrence? How should we think about this recurrence? So it is saying that, what is the interpretation of this recurrence? You can think of it as a mathematical thing, but algorithmically what this is saying is, I'm breaking up a problem of size n into two problems of size n over 2, but the amount of time I'm spending to put the solutions back is what? Not n, but only n over log n. It's a little less, right? Yeah? So, okay, so you say, okay, that's good. I just do the same thing. I'm blind to I'll just do the summation, right? So what should I put inside this? Yeah? Yeah, that you agree? Then is it okay? Okay, now what should I do here? No, wait. Where is n log n going to come? No, that's true. Okay, no, right, that log n levels, but what is the work I do at each node? What do I do here? N by 2? Yeah? That is the thing that you need to make sure you understand. The work I'm doing at each level depends on what? What is the meaning of this recurrence? The meaning of this recurrence is that if I start with a problem of size n, I'm going to break it into two problems of size n over 2, and the amount of work I'm going to do depends on n, so it is n over log n, right? So when I break it into two problems of size n over 2, this is a smaller problem. Now the n has become n over 2, right? Right? So the work done at this node is n over 2 divided by log n over 2. Yeah? Is that clear? Yeah? So what is the total work I do? We have to do some addition. Okay? Now is the addition easy? Little trickier, no? What is the work I do at this level? N over log n. But what about the second level? Sorry? So the work here is n over log n. The next level is what? N over log n over 2. What about the next level? Okay, is the work decreasing or increasing? Sorry?
Not mistaken.
Is it increasing or decreasing? Increasing, right? Okay, now we add this up. Okay. So what do we get if we add that up? You have to know geometric series. I can't help with that. It's even more complicated than geometric series. Right? Why is that? Because my summation is n over log n plus what is this? Can we simplify this? What is log n over 2? Log n minus 1, no? Yeah? What is the next guy? Log n minus 2 plus what do I stop at? Well, you should be careful because you know the base case will blow up if I don't care, right? I have to say it only for n greater than or equal to 2, right? So what do I end up with? With 1, right? Yeah? How does it look like? It looks like a bit funky, no? Yeah? Okay, yes, it is less funky, that's good. So what does this look like? It is n times what? Yeah? Yeah? It is n times 1 over log n plus 1 over log n minus 1, 1 over log n minus 2 up to 1 over 1, right? If I flip it, what does it look like? 1 plus 1 over 2 plus 1 over 3 up to 1 over log n. What is the number? 1 plus 1 over 2 plus 1 over 3 up to 1 over k. What is it called? Summation of 1 plus 1 half plus 1 third plus 1 fourth up to 1 over k. Harmonic series, right? Right? Harmonic sum. So how does it behave? Suppose it is 1 plus half plus 1 fourth plus 1 eighth. What does it behave like? It converges, right? But this diverges, no? How does it go? Yeah, how does what is the sum look like? You haven't. It goes as log n. Okay, 1 plus 1 half plus 1 third plus 1 fourth plus 1 fifth up to 1 over n is roughly log n. Okay, it behaves as an integral 0 to n 1 over x dx. Okay, all right. So, but is this log n or what is this? It is 1 plus 1 over 2 plus 1 over 3 up to 1 over log n. So how should it behave? As log of that, no? So this is n log n. Okay, this is n log n. Okay, okay. See, you know, it was just intended to get your attention because to do these things you need to do some basic summations. There is no go. Okay. Okay. So it is n log n. All right. So first interaction with log n.
So everything that doesn't include the t is
Yeah.
the work.